Hi, I'm Brett Stevens, this is Paul Larson, and this is Ryan Beert, and we're the Brewgineers. For our senior design project, we'll be developing an automated home brewing system.
The automated home brewing system takes the complicated, difficult process of brewing and does what it says, automates it. It allows the user to insert ingredients, press start, walk away, come back in a couple weeks with a full mature beer ready for bottling. The system will automate 3 stages of brewing: wort boiling, cooling, and fermentation. Each of the stages will be temperature controlled with real-time temperature and timing data displayed to the user. Each stage will also be fully customizable with temperature and timing options available to the user.
So this is the project timeline that we've come up with. By week 10, we hope to have a final design of the project that's a complete schematic capture, everything ready to go. And over winter break, we hope to build the system. It's mostly mechanical, getting all the containers together and all the tubing in the right spot. We also hope to have liquid transfer working, so we can open and close the valves and make sure the flow is, correct and everything. We also want to make sure the cooling works. By week 14, we want to have the PCB completely designed and ready to order. That'll give us time to start working on the code and anything else that our project might need. By week 18, we should have our PCB in hand and we can start testing the code, and we want that code to be working and finished. 2 weeks later, we want to make sure everything is put together and we have a fully functioning prototype in which we'll start brewing a beer. And then by week 22, we want to have that beer finished and tested and make sure everything went accordingly so we can prepare for the engineering expo.
So here are a few project requirements for the automated home brewing system. First, the system must be powered from a US standard home, which means it'll input 120 volts VAC, and to ensure that the circuit is not overloaded, the system must not draw more than 12 amps. Secondly, the system must be fully automated. In the first stage, the wort boiling stage, the system must be capable of bringing the liquid to a rolling boil at 212 degrees Fahrenheit. It must keep the liquid at a rolling boil for a duration of at least 1 hour. At the end of this hour, or the boiling stage, the liquid will be transferred into a cooling stage, which will then lead to the fermentation stage. In the cooling stage, the liquid must drop from a rolling boil temperature to at least under 80 degrees Fahrenheit. This is so the yeast isn't affected in the fermentation stage. In the fermentation stage, the system must be capable of keeping the liquid between 60 degrees Fahrenheit and 75 degrees Fahrenheit. Thirdly, the system must display the brewing statistics. So the user must be able to see on the monitor the internal temperature of the liquid, and it'll display the current brewing stage, and will also display the time remaining in the brewing process. This is the top level block diagram for the automated home brewing system. The first input will be ingredient wort. This is all the ingredients necessary for the wort boiling stage. Ingredient firm is all the ingredients necessary for the fermentation stage, and ingredient cool is all the ingredients necessary for the cooling stage. The system will be powered by 120 volt AC power from a wall input. Environment in will consist of primarily ambient temperatures, and user in will be how the user interacts with the system via an interface using knobs and buttons. The output of this system will be beer, which is our most important one, and environment out, which is condensation and boiling temperature. And the waste output will be primarily ingredients that were used throughout the process.
I will now talk about the detailed block diagram. At the top of our diagram, we have the power and control blocks. These interface with almost all the other blocks, and that's why we place them at the top. The power block is responsible for distributing the correct voltages to every other block, and the control block is responsible for getting feedback from the other blocks, as well as controlling the heating element. On the lower part, we broke it up in the 3 stages of wort boiling, cooling, and fermentation. We further broke this up according to their electrical and mechanical components. The mechanical components are going to be the ones doing the actual brewing process, and the electrical components are responsible for heating up the stage, or heating or cooling the stage, as well as feeding back the temperature to the control block.
It's going to be used for communication, and it stands for Serial Peripheral Interface. A couple facts about it. SPI runs in full duplex, which means when you send data, you're going to receive data at the same time. It's synchronous, which means that all of the data and transactions are controlled by a clock by the microcontroller. And it typically has 4 wires. The first main wire is SCK, which is just the clock. MOSI stands for Master Out, Slave In. It's the data that goes from the microcontroller out to any of the SPI devices. MISO is kind of the opposite. It's the data coming from those devices into the microcontroller. And then SS, which stands for Slave Select, and it's active low, and that's how you choose which device you want to send and receive data. So this is how it's going to be used in our project. We're going to have the microcontroller, and it's going to have the 3 first lines that I discussed above, and it's going to have 3 different slave selects since we have 3 different devices. And then our 3 devices, we're going to have 2 temperature sensors, one on the wort heating stage and the other one on the fermentation stage. And then we're also going to have an encoder, which is used for the input from the user to change different various settings. All of the inputs on SCK they're all tied together. They run off the same clock. Same with MISO and MOSI. The way you choose between them, as I said earlier, is by slave select. So let's say we wanted to get the data just from the first temperature sensor. We would hit this active low, and the other ones are still high, so those won't listen on the data line at all. The microcontroller initiates the transfer, data goes out of MOSI and comes in on MISO. One of the main reasons we're using this is because it's fairly easy to use, and a lot of these things have SPI built in.
As Paul previously stated, one of the devices that will be connected to SPI will be the encoders. The encoders are going to be how the user interacts with the system. So the user will be able to make adjustments and customize different settings for the brewing process. The encoders are pretty simple to use. Each encoder will be assigned a 2-bit binary value. So the first encoder will be looking at the 2 least significant bits of a binary value. The second encoder will be looking at the next 2 least significant bits. These encoders will be called in an interrupt service routine. When the encoder is turned, the interrupt service routine will happen so fast that it will detect all the movements of the encoder. In one click of an encoder, the encoder will go through this process of change. It'll go from 1-1 initially to 0-1, 0-0, 1-0, and return back to 1-1 in one click. One click will signify an increase or decrease in minutes, 1 minute or 1 degree in temperature, 1 hour, etc. So to determine whether it's been clockwise or counterclockwise, we will have a variable in the interrupt service routine that compares the encoder value with the variable. So we will be able to determine whether it's turned clockwise or counterclockwise. A clockwise will signify that the value has been incremented, and a counterclockwise turn will signify that a value has been decremented.
One of the features that our project will be using is pulse width modulation, or PWM. PWM is a way to get an analog voltage from a digital source. This happens by switching the digital source on and off quickly enough that the load only sees an average output voltage. The longer that the voltage is high over the switching period, the higher your duty ratio. The higher your duty ratio, the higher your output voltage. So as you can see here, the duty ratio is larger than for the top graph than the bottom graph, leading to a higher average output voltage. So the load will see a higher voltage here compared to here. One of the ways that this can be used is to control the speed of a motor or to dim an LED.